Hello everyone, welcome back to our reading of categories in Sheaves, Kashiwara and Schapira. We're picking up in section 3, in particular chapter 3.1. We're going to be talking about the IPC property today. As you can see, unlike in our usual videos, the words have already been written. The reason for that is because the capturing software that I used to use on my Surface for writing these videos and for recording them has decided it will no longer work with OneNote, which is the software that I used to record this. And I only learned this after trying to record the video. I was very unhappy about that, as I'm sure you can understand. So we're doing it again. And in this reshoot, I'm not going to erase and rewrite everything because that's too much work. So instead, I'm going to just try to explain what's going on here to the best of my ability as I talk you through what's going on in section 3.1. So for a quick reminder where we are, last time, we established that lim as a functor can be thought of as a functor which eats diagrams. That's these guys. And it returns whatever the limit object is. That's, in this case, we're looking at diagrams of R modules, and it returns whatever the R module is that's in the limit. And we saw that this plays nice with finite projective limits. And there was an important part of this argument which required a certain finiteness. And it's annoying because one cannot expect finiteness to be the case for all sorts of indexing categories. I mean, it's just too much to ask for. So in this section, we want to talk about another kind of situation which holds in other situations. In particular, there's a result which we're going to establish here under some notation to be shown, which works well, more generally in some senses, less generally in others. So what's our setup here? Well, throughout, we're going to be dealing with a category which I'm going to call A. That A looks horrible. That's only slightly better, but we're going to run with it. And we're going to take A to be a category that has all of its small products and all small finite inductive, or all small filtrant inductive limits. And we're going to be interested primarily in the situation where we have a collection of such categories, IS. These are going to be small filtering categories. Oh, these guys don't have to have these guys. So we have a collection of categories, IS. These are going to be indexed by some set S, which have to be small and filtrant. And then what we're going to work with is their product category. This will be this guy K here. And K, I know we didn't talk about this, we kind of glossed over in our definitions what's going on with products and other sorts of constructions on the categorical level, but it's exactly what you think it is. The objects of K are tuples of objects in the individual categories. The morphisms are component-wise morphisms, and we just bundle them all together. While we're at it, we have a collection of projection maps. That's these guys. And we're going to call these guys pi s also. And it occurs to me that with my horrible handwriting, I have little s and big S. And this is probably going to be more than a little confusing if they should appear next to each other. So I'm going to do my best to go through as we're doing this and make sure that everything is super clear. Hopefully it doesn't cause any problems, just because they look very similar. But, oh well. So we have our collection. We have a collection of functors, alpha. They're indexed by S, so I could also call them alpha S. And these are going to be IS to A. And when we have this situation, we can bundle all these functors together, and that gives us our guy here, which I call K here. I call it phi. And this functor phi can be written down sort of component-wise by taking the product of all of the pi's and the alphas together. So if I want to evaluate this on some argument, then what I do is given a particular K, then I can write phi of K by taking pi s of K. This lands me in some particular I, and then applying that particular alpha and just product them all together. So this is a sort of formula for calculating with phi. So now the important bit here, and maybe I didn't write enough here to explain what's going on, is there's this object here on the left, this product over all of the limits. This makes sense component-wise. It just does. I can take all the alphas and I can take all their limits over the i's, and then I can product them all together. On the other hand, there's also this family of morphisms on the right, alpha of pi of k, suppressing the s's, mapping into this limit. And so then I can take those guys and I can product all them together also, sort of bundle them together to construct this map, which runs over the product of all the s's of alpha of pi of k to the product, again, this should be over, I didn't write this down, but that's okay, the product over all the s's of the limit of the alphas. And this is going to be the object of our study. So I will box it in and put an exclamation point, because this is the thing we're interested in. So this monster map, which we've constructed, is the object of the following definition. Oh, actually, I wrote down some more stuff here. What's going on here? So, I see. We can take we get this map from this limit, the phi's, into the product of the limit of the alpha s's, and it looks like here all I'm saying is I can then do this component-wise, and I can sort of write down a formula for this as well, where I want to take the limit over now the k and k of the product of all the alpha s's of pi sk, and I map this into the product over the s's of the limit of the alphas. So if you like, this is sort of working with all of k, or on the level of k, if you like. And this last guy here, this is a formula or a component-wise view of what this morphism actually does. I evaluate this by working with each argument one by one. Okay, so actually I think this isn't the morphism I want to study, the one I put in the box. I think this is the morphism I want to put in the box. Sorry about that. This is the guy who I want to focus on. Okay, so now I'm ready to tell you what the IPC property is. So we give a definition, and I apologize for those of you who can't read my handwriting. What it says is let A be as above. We say that the category A has the IPC property if the above morphism is an isomorphism for any family of small filtering categories, and of course we always require S as set. This is sort of a parenthetical remark because we're never really worried about this sort of thing in practice anyway. So first, I should tell you what IPC stands for. This stands for inductive limit product commutation property. And the point of this gadget is that I want, how do I say this? Well, I don't want to jump too far ahead, but what I want to say here is that there is, let me not spoil it. You'll see what this means as we move on. We're going to conclude with a sort of explanation of what this name means in this video. So maybe I just don't get too carried away. So a couple of remarks. Remark one is that this property, this IPC property, this is stable under taking products. This is, of course, what I mean by this is that if I have a bunch of categories all with the IPC property, I take their product, then the resulting category also has the IPC property. And this is pretty easy to see. I just sort of look at my definition. My definition involves taking a product over a bunch of sets. It doesn't really matter what that set is. So if I product more things together, then everything is the same and life is good. The second observation has to do with this thing I don't want to spoil too much, which is that this name has nothing to do with inductive limits and products or their commutation. And we're gonna remedy this. But before I do that, I want to give this sort of prototypical example. Oh yeah, I forgot. I put an angry face here when I was recording because we're mad at Kashiwara and Schapira. So something I wish Kashiwara and Schapira would do throughout is instead of giving hard names or hard facts up front, they should tell us why one should care about any of these things or why one should name these things the way they do, with a bunch of examples, or even just telling some sort of story, and then establish the important properties as a consequence, and then maybe you just appeal to that theorem whenever you want it. But it's annoying to call this the IPC property when it's not obvious what this definition has to do with I, P, or C. And it would be much better if they gave it some different name and then explained what this has to do with anything. But in any case, let's just continue with our example. So the prototypical example is the category of sets. And of course, what's an isomorphism in the category of sets but just a bijection? So what do I have to do is show that the above map is a bijection. So we're going to do that. And in particular, we're going to show that it's both injective and surjective. And this will not be too bad. Injective is slightly annoying. Surjective will be easy. So what I do is I start by taking a y and a y prime in the limit. And I assume that they have the same image under this map U. Oh, I didn't explain my notation. So I have my family of functors alpha s. This is is to set. And then big AS, this is just going to be the limit of the over these s's. And then U is the object we're interested in. It's this limit of this phi, so this is happening up on the level of K. It's the big object, into this product of all of these limits. So U is the thing we need to establish as a bijection. So what we do is I take my guy Y and Y prime, and we put them in the limit, and we assume that they have the same image in the product of the AS's. Now, since K is filtrant, then there's some K, some little k, and a YK and a YK prime, with the property that Y is the image of YK and Y prime is the image of YK prime. Now, if I write this out, well, what does this actually mean if I unpack this, right? We want to use this component-wise idea. So what I do is I write K as a bundle of basically indices. K is a tuple of IS's. And the YK, well, I can write this as a bunch of XI's, and the YK prime, this is a bunch of XI's also, but I'll call them XI primes to keep the notation distinct. Now, for each S, I can look at the pair of guys with the XIS and XIS prime. These guys have the same image in AS, but IS is filtrant. So in particular, that means there's a map from IS, little is, to IS prime, which takes XIS and XIS prime to the same image in alpha S of IS prime. And so what that means is that I can take all of the maps, IS to IS prime, how do I say this? I can take, not the maps, but I take all of the IS primes, and we'll bundle them together, and we'll call them K prime. And then YK and YK prime will have the same image in phi K, and therefore Y will be equal to Y prime. And so that handles the injective part. Okay, that was a bit of a pain, a bit of a mouthful. Surjectivity, I promise you, is much easier. All I have to do for surjectivity is start with my X in the product of the AS's, and I need to show that this is hit, of course. So since for any given S, what I do is I take an IS in big IS and an XI in alpha S IS, that's what you're seeing here, and I want the image of this guy to be XS in AS. The thing is, though, that if I just call the image of the YKs by Y, then, of course, in the limit, that is, then just putting all these together, U of Y must be X. And so we're done. I put the little box. Okay, now, Kashiwara and Schapira leave this to you guys. I'm also going to leave this to you guys just because I started working on it and I got about halfway through it and I was annoying. And I was annoyed because, like, I agree with what they say, but also it's a little bit more tedious because you have to sort of work argument by argument. But what Kashiwara and Schapira say is that this argument will show that set I, set upper I, in other words, the functor category from I to set, also has the IPC property. The exact same argument works. And I more or less agree. You just sort of have to chase through, and for every term, so to speak, in I, you have to sort of check the same argument and then put it all together. This is mildly annoying, but perfectly doable. So we're going to take this as for granted, and I'm going to leave it to you guys to go through and check the details. Okay, so now let's give this proposition that explains this name. So we take A to be a category with these properties, same we've been assuming all along, and we have a set I, and a functor lambda, A to set I. And we assume that lambda commutes with small products, lambda should commute with small filtrant inductive limits, and lambda should be conservative. And under these conditions, we will conclude that A has the IPC property. And this proof is very clean, given all these assumptions. So we'll just show it. What I do is I take my alpha S, my family of functors, again indexed by S, And I consider lambda composed with alpha s. That's these guys. And this, of course, then goes from is to a, and then to set I. Now, lambda commutes with small products and small filtrant inductive limits. So if I look at this map here, then lambda must commute with these guys. And so in particular, what we see is that this is an isomorphism. However, lambda is conservative. And in case you forget, this means that lambda sort of reflects isomorphisms. In other words, if lambda of g for some g is an isomorphism, then g was already an isomorphism. So if lambda is conservative and we've established that this is an isomorphism, then the thing we wanted was an isomorphism as well. And that finishes off our proof. Okay, so a couple corollaries of this, and then I think we'll call it quits here. First is that if C is a small category, then C upper caret, C hat, whatever you want to call it, the pre-sheaf category, also has the IPC property. This is just because, of course, C hat is the category of pre-sheaves of sets, right? It's the functor category. So this is clear. And also, if R is a ring, then we can combine this with what we did last time, and we see that mod R also has the IPC property. And I sort of suspect, as a sort of motivation for where we're going with this, like the reason for this, is because I should be able to put these things together and do something like this with schemes, and sheaves on schemes. I don't really know 100% for sure, because, I mean, when I learned sheaves on nice objects, I mean, everything was topological spaces, and now everything here is categories. So I'm not completely sure that the story checks out the same, but my guess is that the reason that we're doing this is because Kashiwara and Schapira want to eventually tell us what their notion of a sheaf on a reasonable space is. They want to talk about sites or something like that. And my guess is that the purpose of all of this is to establish that I can play the same game where instead of working with R modules, I work with the replacement for modules over a ring, which will become sheaves of modules over the structure sheaf on some reasonable kind of space or on some site, yada yada. And my expectation is that what we're going to establish is that these properties continue to work in those settings as well. But I'm not sure about that yet. I mean, we're going to have to just sort of wait and see. We're only in chapter 3, and I don't think they're going to tell us what like a growth-unique topology is or how any of this actually works until like almost the end of the book. So hopefully future viewers will be able to watch this story through in its completion. But I mean, hopefully you guys know by now that I won't let too long go by without drawing you a picture or showing you something useful to sort of explain what the heck is going on here. So I think I'm going to wrap it up here. I think this is going to be enough for 3.1. We'll pick up next time in 3.2. We're going to talk about filtering categories. We'll probably skip the first bunch of stuff, or maybe if I don't skip it, I'll just summarize the results because I've given some of them as examples. Some of the things are sort of clear, but we're going to collect some important results about filtering categories and then continue to develop some theory. Okay, guys, hopefully you've enjoyed this, and I'll catch you all in the next one. So until then, take care.